Hi guys, so in this video we're going to go through more of the specifics of compactness on the real line. And again, we're defining compactness to say that the set X is compact if and only if X is closed and bounded, even though this isn't your standard definition of what compactness is. You can define it this way because it's an equivalent condition on the real line. On a general metric space or general topology, that is not the case. So X is closed if and only if its limit points are contained in X. If and only if X closure is equal to X. That's another characterization. And this is also like saying for every y in R, for every epsilon greater than 0, there exists in X such that y minus X is less than epsilon, implies that y is in X. So, and another way of saying this, probably a better way of saying this, is that the limit as n goes to infinity of xn equals x with xn in X for all n tells us that X is in X. This last one is probably, if you haven't taken an analysis class, it's probably the easiest way to think about it. If you're taking an analysis class, this is these last two are probably relatively obvious to you if you work through the definitions at least. So remember from our last example, from the analogy in the last video, that we wanted to say that the set X here was when we had a valid price. What we said is, if I take the sequence of those prices, I'm going to untaxed. Then that set will actually be compact, or it will be closed, because if I take a sequence of prices untaxed and they converge, well, I'm going to get a valid price. But if I scale it according to the sales tax, well, I can get a fractional digit and I can still converge, but I'm no longer a valid price. And so the set was not closed. So let's go through some examples here, and I'll go back to the same that's not a great example. So, actually, this is a good example. So, for X in R, this is our whole space. This is our whole universe. So, if I have a convergent sequence, then it has to be in R. That's our whole universe. So, by this definition, we have that X is closed. Now let's take some more interesting examples. And these are probably the easiest ones to think about, is what you can do with intervals. Okay, so basically, another way to think about closed is that its limit points are contained in X. So limit points are boundary cases. So it's kind of like saying that the boundary of X is a part of X. So let's think about this example where we take the closed interval, and this is just as a review. Closed interval 0 to 1 is when we have 0 less than or equal to X, which is less than or equal to 1. So I need to, let's get two colors here to make it easy to see. So this is the closed interval 0 to 1. So we have to ask the question of, let's think about it this way. The boundary of X is part of X. So the boundary of X are these 2 points here, 0 and 1. So the boundary is equal to 0 and 1. And so we ask the question, is 0 in, question mark, 0, 1, and is 1 in 0, 1, question mark. So you can pause it here and think about it for a little bit. How is X defined? Well, 0 is certainly less than or equal to 0. So 0 is in X. So we're good there. That part of the boundary is included. We have to check the other part of the boundary. 1 is certainly less than or equal to 1. So also 1 is in X. So that tells us that X is closed. For a second example, let's cut 1 out. So this is now the set of all X in R, such that 0 is less than X, which is less than or equal to 1. Does this contain its boundary points? Well, we do the same test. 1 is less than or equal to 1. Right, so the boundary, yeah, let's go through the work in white. So the boundary, oh yeah, sorry, I didn't, it's this set right here where we put, so this set now is a hole at 0 and not a hole at 1. So the boundary is 0 and 1. So 1 is less than or equal to 1, which is good in our definition. That tells us 1 is in X. But now we have a strict inequality here on this side. 0 is less than 0 is not true. So 0 is not in X. So let's call this the whole boundary. Every boundary point has to be in the set. If there's one exception, it's no longer closed. It's not defined as closed. So X is not closed in this case. Similarly, and you guys can pause the video here to think about this before I give you the answer. So this looks like 2 holes here. This one's closed, but open here. Oh, gosh. So 1 is not included in the set. You can pause it here, think about it. before I give you the answer. So this is not closed because 0 is not in X. Also, 1 is not in X, but you only need to show 1. This is also not closed because 1 is not in X. And then I'll show you guys a final example where we consider 0, 1 union 1, no, not 1, 2. Let's do 2, 3. So this is the set 0, 1, 2, 3. So we look at the boundary here. We have this point, this point, this point, and this point. That's our boundary. And so clearly, based on this definition, 0 is in X, 1 is in X, 2 is in X, and 3 is in X. Oh, sorry, is in X. So it's closed. And then similar to what we did before, if we take another union of an interval, but we cut out the 2 here, you can pause the video here to think about whether this is closed or not. This is not. It's not going to be closed because 2 is not in the set and it's on the boundary. Okay. Now we're going to go back. We're going to ask if certain sets are compact. So remember that compact is the same as saying closed and bounded plus bounded. And bounded, if we recall, this is the easier of the two conditions. Says that all elements have absolute value less than a fixed value. It can't go, nothing can go to infinity. Equals no sequences in X can go to infinity. And this is saying there exists a number m such that for all x in X, the absolute value of X is less than or equal to m. And yeah, so let's just go through some examples. So for example, if X equals the integers, you can pause and think about this because I think this definition is easier to think about. So I'm just going to take the integers, right? These are real numbers. You can pause it here and ask yourself if it's bounded. The answer is no, because I can take the limit as n goes to infinity of n, and that's infinity. I found a sequence that goes to infinity, so it's not bounded. If I take X to be the set of all X in Z, such that X is such that the absolute value of X is less than some fixed n, is that bounded? You can pause it here and think about it. The answer is yes. I've directly built it into the definition. Right, those are basically saying the same thing for all X. Okay, so compactness is just having both conditions. I'll give you one more example. this is also built into the definition. Yes, the absolute value of x is less than or equal to 1 for all x, x, and x. So we need both of them to be true to be compact. So let's give an example of, they're not the same thing. So let's do closed and not bounded. A good example here is just x equals r. It's the whole space. Right, if its boundary is empty. So clearly, because infinity and minus infinity aren't numbers. They're not defined. So we say, well, it actually doesn't have a boundary at all because these aren't numbers. So this is clearly closed. But I can take the limit, again, I can take the limit as n goes to infinity to just n. That's infinity, so it's not bounded. Let's do not closed and bounded. Well, let's take x equals 0, 1. Clearly, the absolute value of x is less than or equal to 1 for all x. Let's draw a line between these. I'll change a different color to differentiate these. So for all, oh yikes, for all x in 0, 1. But it's not closed because the boundary is the list 0, 1 here, and 0 is not in x. Not closed, not bounded. So let's take, this one might take a little bit more thought. And you can pause the video and think about what you can do here for this to happen. So what I'm going to do is I'm going to patch a bunch of not closed intervals together. And I'm going to do n plus a fourth, just to be safe. You can do n plus a half. I'm pretty sure. I just want to be safe that they're disconnected. So it's not bounded. Because the limit as n goes to infinity of n plus an eighth, right? And n plus an eighth is in each one of those sets, so this is a valid sequence. That's infinity. So I found a sequence in the set that goes to infinity. It's not bounded. It's also not closed because, let's see here, n equals 1. Yeah, sorry. For boundedness, if you find a sequence that also goes to negative infinity, it's also not bounded. Because you're thinking about things in absolute value. Sorry. So there's a misstatement from previously in the video. So remember, you can also take sequences that go to negative infinity to show that something's bounded. Not bounded. So it's not closed because 1 is a boundary point. And if you don't understand why, pause the video and think about it a little bit longer and go back to this example. So we're just looking at one particular, so we have sets that look like this. There are a bunch of open intervals with gaps in them. So the boundary, 1 is there, it's still in the boundary. That's the way to think about it, if you're not entirely sure why that's the case. But 1 is not in the set because we cut holes out there. Yeah, if you prefer, this is open intervals that look like this. Whichever way, they mean the same thing. And then finally, closed and bounded. So I'll give you 2 examples here to show you that they don't necessarily have to be connected. So this is closed and bounded. the boundary, or we've already showed why it's closed, but also clearly it's bounded because everything's less than 1. Another example, so this means it's compact. And then just for emphasis here, the set doesn't have to be connected. So this is, and it'll still be compact. So this is 0, 1, 2, and 3 on the real line. This is closed. So the boundary is the set 0, 1, 2, 3, and those are all in X. So we're good, it's closed. It's also bounded because the absolute value of X is less than or equal to 3 for all X. So that tells us that X is compact. And then in the next video, I'll talk to you guys about, we'll go back to that pricing example, and I'll explain about another definition of compactness that's the more general one, the more interesting one to some extent, than just on the real line.